differential equations. By the way, the homework that's due Tuesday, I said that there was a data set. Did any of you find it on the website? No. It's on the website. It's E792 or something like that. .dat. If you don't find it, send me an email. But it should be there because I rolled it up on that. So you need it for the second problem. All right. We're now ratcheting up. We're starting to move more towards the science and engineering type problems that you're going to commonly encounter, particularly in the upper level courses. There are a lot of techniques that are used. There are three methods that I want you to be familiar with as far as solving ODEs. Euler's method, Kuhn's method, and Runge-Kutta. And it's particularly the fourth order Runge-Kutta that I want you to be aware of and to know how to do that. All right, you're going to be solving ODEs of the form that looks something like this, either first derivatives or second derivatives. All right, what's the difference between this and a partial differential equation? I'll give you a hint, it's the D. Right? If you have a partial, all right, it's going to mean it's going to be a function of multi-space or whatever. Right? Okay, one-step methods, commonly used to solve equations of this type. They fall under this category called the Runge-Kutta. Right? That's the general categories. All right, Runge-Kutta. If you go in and look at a reference, you'll find all kinds of different types of Runge-Kutta methods. Second order, third order, fourth order, eighth order, whatever it is. The most commonly used one is a fourth order. All right, multi-step methods. You use information from several previous values as a basis for determining whatever the new values would be. What's that similar to? An iteration. Right? So you're using previous information, you're going to keep building on it, and ultimately getting the solution. We refer to those kinds of techniques as predictor-corrector approaches. All right, now you have a second order ODE. First thing you're going to do is probably panic because you say, at some time, I think I remember when I took ODEs of how to analytically solve that. Right? Well, now you don't solve that. Now the computer's going to do that, but you have to be clever enough to realize, okay, what's the techniques that are going to be the best for solving these kinds of equations. You notice what I did right there? What happened? What did I do from this equation to that equation? What's the order?
You change it from second to first.
It's a second order to a first order. What did I do? I did a substitution. Is there anything wrong with that? Not that I know of. I think mathematically it's still valid, still works. So we converted that second order to a first order. All right, so you have two first order equations that define the second order original equation. You have that one and you have that one. All right? Now, before computers, ODEs were solved by integration techniques, right? What mechanical device did they have for solving things? Say what? Slide rules. Anybody know how old the slide rule is?
Oh yeah, the slide rule.
There's actually, I think, a form that was used by the Egyptians, if you can imagine. Okay. Exact solutions for many ODEs are not available, particularly when you start dealing with nonlinear equations. That's why you're taking this course, because you're going to run into problems where there are no closed form solutions, no analytical solutions. You're going to have to do it numerically as an approximation. All right, first method. It's called Euler's method. Very simple one-step method. All right, here's the first derivative, dy dt equal to a function of t and y. All right, I can rewrite this so it looks like this. How did I do that?
I have no idea.
How did I go from that to that? Sure, Taylor series. All right, you've already seen it. How do you solve for the first derivative as a forward or backward difference? From Taylor series. What did I do here? I did a very simple one-sided difference, right? And so I just set it equal to yi plus vh. Phi is the increment function, that is It's a slope, right? It's the same thing as the Taylor series. All right, so phi is a function of ti and yi, the one-step equation. Ultimately, it looks like this. So that phi is really this. All right, what's h referred to? The step. The step, right there. Right? That's like a delta t, or whatever that h is. That's that delta. That's what I'm going to be using. All right, that's called Euler's method. It's a point slope method. All right, remember, you have to obtain the slope. Then you use it to predict the new values. You're using a step size h. Circle that one several times. That will come up again, probably on quiz 2. All right, Euler's method, what's going on? Here's the true solution. This is our approximation. Why does it look like this?
So it goes right off the slope.
Because it was linear, right? Very simple approximation, one-sided. So that point to that point. So what's my error? The difference between the true and that. How do I refine that error? How do I get it smaller? Smaller h, right. And in fact, Taylor series tells you that. Okay, example. Integrate y prime equal to 4e to the point t minus 1/2 y. And I want to go from 0 to 4 using a step size of 1. All right, I start with an initial condition. I have to start it with something. Right, unless given, what do you assume? 0. Right, okay, so let's start with y equal 2, t equals 0. So you just plug in the numbers, solve for the function at 0 and 2. All right, so here's the slope. Plug it in, you get 3. So first step, right? I get a value 5. What's the true solution? Okay, so I know what the analytical solution is. I plug it in. It's actually that. So my first rough estimate using a very crude h of 1, I get about 19% error. All right, I go to the second step. What am I going to do? Now I'll plug in this function at 1 and 5, right? I bring that down here, plug it in. I now get 11. Hey, what's going on?
Well, good question, sir.
Sure.
Your limits are from 0 to 4, so why would you use 5? You know the 5's automatically wrong, right?
No, that's just my first estimate. Here's the true value. All right, I'm integrating.
The x is from 0 to 4, y
Yeah.
is.
Yeah.
So in this case, you use the definition of the function in order to find the slope?
See right there? I'm evaluating this at the initial conditions, y equal 2 and t equal to 0. Okay? So that's what goes in right there. Okay? Now I'm going to update this. What's this remind you of about updating? Gauss-Seidel, right? All right, so you see in this course how things kind of keep building on each little step that you do, and you think, oh, we did that before. Maybe it's called a little different technique. Same idea, same thing here. All right, now, so we notice, something suspicious here. What's going on? All right, so you compare the true solution with that for what you get with Euler's method for this. All right, initial condition t equals 0, y equal 2. So what's going on? Here's the true solution. Here's Euler's solution. What's happening as we go further and further out? Yeah, the error's building, all right? But what is our approximated solution doing? It's trying to follow at least what the true solution does, but we're going to start diverging further and further away from it. That tells us something right off the bat. What do you think it is?
More accurate or closer for smaller?
Smaller intervals.
H, it tells you right off. H, maybe my H is too big, right? Okay, the error is considerable. Computation, however, captures the general trend of the true solution, as we saw. All right, here are the two kinds of errors. Circle these. The first one is called truncation. The second one is called round off. Truncation. You know what that is already from Taylor's series, because it's the truncation of the approximation. You've truncated it or stopped it or said, this is as far as I need to go, as far as that accuracy. All right, the second one, round off. What's round off due to? Right, That's inherent in the platform or the computer that you're using. Right? That's how many significant digits is the computer that you're using retaining. So if you're running a PC at 32-bit versus one at 64, what do you think is the difference going to be? It's going to be a lot more accurate, obviously, on the 64. Why is there a push nowadays for 64-bit computers?
They run games better.
Because Bill Gates says, I want 64-bit. Okay, we'll do it. Actually, the 32-bit, if you wanted to get the equivalent accuracy, you'd have to do double precision. And double precision, I can guarantee you, will be exceedingly costly on those lower-end machines. So that if you're running on a 64-bit, that's pretty darn good. All right, local truncation error results from the first step. You notice that error began immediately, and as we proceeded with the next step, the error got even larger. All right, it's the sum of the local and propagated errors. That's what's going on. All right, local error associated with Euler's method is second order. Global error is order H. All right. Global error, how do you reduce it? Step size. So you tell right off by calculating the error, oh, I see what's happening. I'm going to have to cut back. All right, here's an M file if you want to run Euler's method. It's not very long. Actually, you could probably come up with something even simpler. Every year, MATLAB revises and updates and comes up with new subroutines and so forth. I think you can do a simple EUL or EULER, whatever, and it'll do an Euler for you right off the bat. But anyway, that's how you would set it up, kind of the old way. All right, Kuhn's method. This is an improvement to Euler's method. The derivative at the beginning of the interval is assumed to apply across the entire interval. All right? So that's Euler's method. So you have one derivative. You're assuming that's going to hold everywhere. But now you're going to say, hey, wait a minute, I'll do two derivatives. One at the beginning, one at the end of the interval. Understand? Okay. Two derivatives are then averaged. You get an improved estimate. All right, makes sense. One at the beginning of the node, one at the end of the node, I average, I go to the next interval, I do that again. All right, this is known as a predictor and a corrector. All right, two-step process. Okay, first step, it looks just like Euler's method. Second step, okay, I will do this, I will average these two values, and then we'll see what we come up with. It should be an improvement. All right, so here's a predictor, right? That's just Euler's method. Here's the corrector. So I'll pick up on this one. So now I've got an improved slope, obviously. All right, let's go back to this example. And we'll use the same step size of 1, initial condition y equal 2, t equals 0. All right, use 1, 2, 3, 4, epsilon equal 10 to the minus 5 to terminate the corrector iterations. All right, first step, right? What did we get before from Euler's method? Same thing. So it's Euler's method. All right, now we do the predictor. All right, so we compute a value of 1, so we get that. All right, now improve the estimate, throw it in here, right, 6.4, so now I average 3, 6.4, 4.7, I substitute that into the corrector, all right, I get 6.7, right, let's see what happens. Next step, all right, now we'll go into the corrector here, so here I go back and I'm going to evaluate now with this improved calculation, average. I get 6.27. What's my error? Okay, what do we have before? 19. Right? All right, next iteration. 1.66. So what does this tell you? It's significantly improved. But what have I used? The same H. All right? So I haven't had to go in and double the amount of calculations because I had twice as many intervals. You could do that versus an Euler's method, which is a one-step approach. but maybe doing this two-step may be much quicker, a lot more efficient. All right, 12 iterations, the error falls below the stopping criteria. How do we find truncation? Right, just like you do in Taylor series. So this tells me my truncation error, h cubed over 12 times second derivative. All right, if I divide by h, right, like I do in a Taylor series and finding a derivative, the global error would actually be h squared, all right? Does everybody understand? Local error, global error. Global error is like finding the derivative on a Taylor series, you divide by h, remember? So your truncation error, the highest term is divided by h. That's why it's second order. But if I say, well, what's the local truncation error here? It'd be h cubed. That's because I haven't divided through. That just tells me these are the terms that are coming out from these series. All right? So Euler's method, global was what? H. This one, h squared. So I doubled the, well, not doubled the accuracy, I improved it by an order of magnitude. Okay, graphical representation, what's really going on? It's kind of this closed loop. You calculate this value, you take that latest value, you throw in there, you average, and you just keep doing it over and over and over again. And it converges quite rapidly. All right, midpoint method. This is a simple modification to Euler's method, just to make you aware of it. Actually, what I'm doing is what? Having the interval. That's simple. All right, so I calculate a new slope, put that into here. All right, corrector here cannot be applied iteratively to improve the solution as we do in the previous method. All right, all you're doing is just saying, oh, I'll just have the interval size. And I know that has to improve my error to some extent. Midpoint method is better than Euler's method, produces local error h cubed, global error of h squared.
Just by having the interval?
Just by doing that. Just by bringing that down. That's what happens. All right? Which method would you prefer though?
Midpoint.
All right. Think. Now, you're going to, in the practical sense, am I going to run a simulation that takes 2 steps, or should I run one that's going to be h divided by 2, although it's double the amount of steps I'm going to do? So what's the trade-off? See what I mean? So at some point you may say, sometimes the simplest method is the best method, even though the accuracy may not be quite as good as an improved method. All right, here's the midpoint method. Remember what this would be? That's Euler's method. So what I'm doing here, okay, I'll just have it. So in this very simple case, it looks like Lind's method. All right, now, let's get to Runge-Kutta. Now, before we get to Runge-Kutta, everybody understand Euler's method? That's the important one, that very simple approximation. If you want to improve it, you have 2 ways. Remember? One is the h over 2, the other way, Lind's method. All right, just find the slope at the 2 endpoints of the interval. Runge-Kutta. This is what you'll find most commercial codes will be using as far as doing these kinds of solutions. It's just efficient and works very well. All right, this looks just exactly like what? What we did for Euler's method. All right, so a very simple one-sided approximation. All right, the slope or incremental function, right, we can write it in this general form. Now, a1, k1, a2, k2 plus dot, 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 all the way out to an, kn. So I could run this out to infinity if I wanted to. What am I going to do? Just like a Taylor series, I may say, okay, I don't want to run all those steps, so I'm going to truncate. So I'll do this. K1 will be the value of the function at the initial conditions. Then I will do this for K2, I'll do this for K3, dot, 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 all the way down as much as I want. Now, you may say, what's this? Right? These little terms right here are what make this unique and why you can come up with different orders of accuracy with Runge-Kutta. The general thing to remember is this, right? Actually, if you take that expression and circle these, then you will have Runga Kutta. You won't have to worry about trying to remember all the details. It's just this and this. That's the important thing as to what's going on. Every time you build up, right, you keep, it just adds more and more. You can see the pattern, I think.
Where did the constants come from?
Okay, I'll show you. That's what we're going to do. P's and Q's are constants. K's, these are known as recurrence relations. Right? Now let's see what's going on. If I want to run a second order Runga Kutta, I would only have A1 and A2. All right? Kind of makes sense. Now, what would those values be? So here's the general relation. Here's the first initial value. Here's the second, right? P1, Q1, 1. Now, values A1, A2, P1, Q1. Evaluate by setting the relation here equal to a second order. Aha, there it comes again. Taylor series. See, you can't get away from it. Should have called it. I ought to come up with my own series. Everybody. All right, so how do you do it? Easy once you see the pattern. The combination of the coefficients here always equal 1. So I have A1 plus A2 equal to 1. All right? So I know if I have if I have A1, I'll find A2 or vice versa or whatever. Right? So if I do it this way, A2 P1 is equal to a half, A2 Q11 equal 1/2. Aha. All right? You can choose an infinite number of values. Obviously, what's the deal here? You go, well, yeah, how many numbers do I want to choose? Well, an infinite number is fine. I'm pretty safe with that. Infinite number of second order Runga Kutta methods. Now, I don't know if that helps you or hinders you, but you're going to see an example of the one that I want you to remember. All right?
Where did the 1 happen?
Well, it's because, okay, let's start and set this up through the Taylor series, and what we'll wind up with is a half. If you go through and you say, oh, I see, it really has a basis in the Taylor series. Now, let's let A2 equal to a half. All right? So if A2 is a half, do we know what A1 is going to be? Sure, it's going to be a half. All right, so here's the formula. All right? 1/2 K1 plus 1/2 K2 times H. All right, so here's K1 right here. Here's K2. Now you notice I'm evaluating K2 at the initial condition plus the H, and at Y, what that K1 is times H. All right? If I wanted to make this a midpoint method, all I'd have to do is let A2 equal to 1. All right? So what happens? Oh, that's the same thing as we just saw. It's H over 2. Right? So you see why these things are generally called the family of Runga Kutta methods. You can get almost anything out of them. All right? Ralston's method. We said let A2 equal to 2/3, A1 equal to 1/3, of course. P1 equal Q11 equal 3/4. All right, so there are a lot of these things in various tables and books that you'll say, my gosh, how far do these things go? You know, they can get out of hand. Now, this one, the second order that I had up there, where A1 and A2 are both equal to 1/2, circle that. That's going to be important.
Which one?
This is the other
A1
one.
and A2.
Definitely double circle that one. That's a fourth order Runga Kutta. All right, so fourth order, I'm going to have K1, K2, K3, K4. If I wanted to run a sixth order, what would I have? 6 Ks, right? All right, here's K1, here's K2, which we've seen before. Here's K3, here's K4. All right, now it turns out that that fourth order method is very similar to Simpson's 1/3 rule. You ought to go back and take a look at Simpson's 1/3 rule. Remember H times 1 over 3? What's the other Simpson's rule?
3/8.
3/8. You got it. All right. The K's are the slopes. Okay. Here's this little relationship. Let's evaluate it. T equals 0 to 1 with a step size of 1. Initial condition 2. All right. Let's see what happens. Calculate K1. So f of 0 and 2, plug it into the relation, you get 3. We've seen that before. From where? Euler's method. So you see, if you know Euler's method, you can get started on this one. You got the first one. All right, compute value of y and a slope at the midpoint. Okay, plug that in, we get 3.5. K2 now. So here is 3.5. We evaluate the relation now with this, 4.21. That's the new slope. Plug that in. Now calculate K3. Plug that in. 3.91. Now, new value of y in the slope, 5.9. Plug that in. 5.94. All right. You now combine them to yield the average slope. All right, now calculate phi. So, that value, right, that's the first value, right, in K1. 1, 2, 3, 4. So we get 4.2. Right? Plug that in. Now we're ready. Let's do the calculation. 6.20. Compute the error, which is actually 6.19 minus, okay, compared to 6.2, what do we get? 0.103%. Right? What did we get initially with Euler's method? 19. Okay. What happened when we improved it? 6 or so, or somewhere. What do we get with this? Okay. How much computational work did we have to do? It was 4 steps. Okay. What do you think is going to happen when you set that up in a scalar mode on a computer? It'll be done in nanoseconds, right? All right. If I want to go to a higher order Runge-Kutta, called Butcher's method, I guess. I guess that's how I can say that. A lot of these guys are German, so you have to get the German accent. Okay, so now I would have K1, K3, K4, K5, K6. All right?
What happened to K3?
Yeah. What happened? 1, 2, 3, 4, 5. That's why it's called his method. It's a little variation. You take the 2 plays into the 3, but not into this. So sometimes there's slight variations, right? And that's why it's called that method. All right. Adaptive Runge-Kutta methods. These automatically adjust step size. The nice thing is on a lot of the commercial codes that these things will go in and set up for you. You input the initial conditions. In fact, that's one of the nice things about MATLAB. You set up the initial conditions, make the call, and it'll do all that for you. But be very careful. You're treating that like a black box, and whatever comes out of that black box has got to be correct. Right? That's why you have to know, well, what is the engine? What's going on here, right? What's happening? So here's Euler's method, Hund's method. This is a 3rd order Runge-Kutta. If I run a 4th order, or I run, say, that 5th order by this guy, right? Now look at the percent of relative error. What I'd really like to do is be around in here. I don't need to go any further than this, particularly as engineers. You're wasting cycles. Are you sure you want to get something out to the 4th or 5th decimal place on this thing? You think they're going to see that in building this new science and engineering building? I probably not even order of magnitude if we're lucky. All right, so this is the most preferred, that 4th order Runge-Kutta. All right, so what's going on? Here's K1, calculate this slope. There's K2. That, if we did that projection, that would be what? Euler's method, right? Here would be K3, using information from K2. Here's K3, I get from this, here's K4. Aha, what am I doing? You see these arrows? What are they doing? They're correcting, right? And they're trying to correct this thing down to the true solution. That's what it takes to ultimately correct this. And you wind up getting a really accurate simulation. All right, so here's a 1-step method. This would be Euler's method. Right, so you say I've got 2 values. I do a linear approximation on this. Okay, this is the slope I get. Probably not real good. However, if I start picking up additional points and I can reflect that into these higher order Runge-Kutta methods, I'll do pretty well. All right. What I want you to do, finish reading this business on Runge-Kutta methods. Be sure you can do a very simple problem using Euler's method. Right? If I ask, how would you improve it? You know of two ways to do that. If I ask, do a second order Runge-Kutta, you should be able to do that. Now, why would I say second order versus fourth order? Yeah, because it takes too long to run out some of these higher order schemes. But if I say, describe or list what it is you would do as a fourth order Runge-Kutta, be sure you can do that. All right? Okay, now, next week, we're going to start on least squares. We're going to start moving into some statistics. Has anybody had a statistics course before? Maybe we'll have you guys teach. No kidding. So you guys are statisticians, bona fide card carrying?
He's card carrier, I'm apprentice.
All right. Good. We might have you guys do that maybe in a week or two. We'll see where we stand. If I may try to get Angelo Infantis here, who is the statistician within the college. He's also the guy that wrote the gaming algorithms for Nevada Gaming. He's the guy that does all the video poker, all those sorts of things. He wrote the algorithm for it. He says no one can break his code. I think, did he just challenge us? Who's he kidding? We've got a super here. Eventually we could probably break it, but he says it's unbreakable. So was the Enigma code, but I think that was broken too.
Yeah, by Colossus.
Yeah. All right, any questions? Okay. Thanks. See you guys next week.